Hello students, welcome to my channel again. In the previous lecture, we were discussing about the Einstein theory of radiation, and we developed a set of equations and we obtained the important conditions that are necessary for the lasing action to take place. And these conditions were that number one, there must be a state of population inversion in the laser medium. Number two, a continuous supply of external energy must be established so that the population inversion must be achieved as well as maintained over the desired period of time. And that second condition or the second process was called pumping. And the third condition was that it is preferably good to have at least one metastable state just below the what we call as to be normal excited state. And this metastable state had a lot of advantages over the two-level system, and these advantages I discussed with you in my previous lecture. Now I would continue my discussion from the previous lecture that we just got the knowledge of one metastable state. However, if there is another level just above the ground level, then the working of the laser becomes even more, let us say, quality-wise, it improves. Let us see how it is important to have another level just above the ground level. Let us assume this is excited level having energy E2. This is meta state, its energy is E2 dash. This is ground level G, its energy was taken to be E1. And let me take another level here. This may or may not be a metastable state. Let me take it to be a level called as L, and its energy is, let us say, is E1 dash. Now, in the previous case, this level L was not there. How the different levels are achieved? It is a property of the material science. It is a topic of the material science. You can just remember that when we add appropriate material into another material, then new energy levels are created. You might have the knowledge of this concept in your higher secondary classes at the school level, that when we added N-type or P-type impurity into a pure silicon material, then there was creation of additional energy levels. The level in case of N-type impurity was called donor level, and the level in case of P-type impurity was called acceptor level. And I will not go into the detail that why donor level is created just below the E level, and why valence and why acceptor level is created just above the valence band. So this is something which is outside the scope of discussion in today's lecture. If the time allows, I will be just giving lectures on the topic of semiconductors also. For the time being, we can just remember that the new energy levels can be created by adding appropriate materials in the given material. Okay, the pumping process was taking electrons from G level to E. This is a part of my previous discussion. I hope you might have attended that lecture, and therefore you will not find any difficulty in understanding the concepts that I am discussing right now in this lecture. So from here to here, the electrons came through spontaneous or non-radiative process, and the energy lost, that was E2 minus E2 dash, is wasted as heat. So from in the previous discussion, the lasing action was between M level and G level. So M level gave us lot of advantages. However, one disadvantage is still there if there is only M level and no L level. That was it cannot create instantaneous action of the laser. We still have to wait for the time so that population inversion is created by the pumping mechanism. So it means there will be still a time gap between the switching on of the switching on pumping and the coming out of the laser light, because one metastable state just below E level cannot make the laser function to be instantaneous. Now let me take another example. Suppose it is just a supposition. You can take any desired value. I am taking sometimes 100, sometimes 80, sometimes 20, sometimes 1000, sometimes billions and trillions of atoms in the material. It is just to give you some demonstration. So you can use any value which appeals to you for better understanding. So let us say there are total of 100 atoms per unit volume. So as per previous discussion, you cannot get population inversion till at least 50 of the atoms are excited. So till then we have to wait for the laser action to start. So now suppose this level L is available, and let us say pumping has just started, and in very small interval of time just after starting, let us say it has only excited 5 atoms. So 95 atoms are still in the G level. So since the atoms are being excited by the pumping mechanism from G to E, so these 5 atoms will go to the E level. Since E level is short-lived, I will take just an example. So therefore, out of these 5, let us say 1 is in the state E, and due to fast decay, 4 reach at M level, which is a metastable level, so which is a long-lived state. Now, please remember, if L is not there, then 4 is smaller than 95, even 1 is smaller than 95. You cannot get laser action between M and G or E and G. However, if we have any other additional level present just above L, then what is the benefit of this? That this level L will have 0 occupancy. Now, please remember that 0 is smaller than 4. So, although pump has not excited more than 50% atoms in the material, even then population inversion will be established between M level and L level. So as a result, when one of the photon, let us say, decays after spending whole of the time, that is 10 raised to power minus 3 seconds, and it will travel in some direction. This photon, since it has it came just because of covering its whole of its lifetime, therefore we will call it to be seed photon, and it is spontaneous in nature. Now when it will just come here, it will release a photon. The energy of the photon will be E2 dash minus E1 dash, and therefore the total number of atoms here will be 3, and this occupancy will become 1. Now this photon, which is spontaneous in nature, it is traveling in the material, and when it is traveling in the material, let us say it strikes with some atom. You kindly remember there are still 3 atoms which are in the state M. And why these are 3 here? Because all these atoms were not let us say appeared at the same instant of time. Out of these 4 atoms, 1 atom was created due to the excitation at an earlier instant of time, other at later instant of time, and so on. So the one which came first of all in this state will produce a seed photon, and that seed photon will travel in the material, and during traveling it may strike with one of the atom which is still in the M state, because its time is still lesser than 10 raised to power minus 3 seconds, means it can manage to stay there for some more time. However, when seed photon strikes some atom which is in the state M, then due to collision of this seed photon with this kind of atom, the second atom with which this collision takes place will eject a photon, and that photon will also be of the energy E2 dash minus E1 dash, means that excitation will be a stimulated excitation. So this photon is a stimulated photon. This is the seed photon coming from backward or initial, which has triggered the stimulated process, and as a result the process of laser emission will start between E2 dash and E1 dash, even when you have not got the population inversion between G and E or G and M. So therefore the lasing action can start in principle as soon as we will start the pumping. The lasing action will start immediately. So therefore the presence of another level just above G gives us an added advantage. It makes the laser function to be let us say instantaneous. Now if you assume that when all these 4 photons will be emitted, then this number, let us say, becomes 0 and pump is on, and these will reach here 4, and this 4 is less than 4 is greater than 0, and one may expect that there will be some population inversion will stop and the lasing action will stop. Actually it is not going to happen, because we can just bring these 4 atoms back to G level artificially, and this process, that when atoms are brought from G to L artificially or forcefully, such a process is called induced de-excitation. So kindly remember, this induced de-excitation is a process which we will be just forcing, so that as soon as a de-excitation from E2 dash to E1 dash takes place, immediately that atom is brought back to G, so that this atom always shows 0 population, and since pumping is on, these 4 atoms will come here. This will become principally 99, but because pumping is on, in the meantime pump might have excited some more atoms to E, therefore this number will become less. So 4 have de-excited, in the meantime let us say 10 more have been excited, so therefore there will be 80 out of 85 out of 95, 10 will go here, and out of 10 let us say 2 stay here and 8 come here, and again you can see this 8 number is greater than 0, so therefore the intensity of the light will grow. So when the intensity of the light will grow, because previously the beam of the light emitted was, as per my example, was due to 4 de-excitations. Now this beam can be due to 8 de-excitations. Kindly, again I am repeating this, kindly note that the process will not stop. The lasing emission process will not stop when half of the atoms will come here. You cannot say that it will be 4 here and 4 here, because if it is 4 and 4 here, then population inversion will cease and the spontaneous emission will start dominating. But actually, due to the artificial de-excitation or induced de-excitation, when 4 atoms will de-excite, this number will still be 0, and as soon as these four atoms are obtained in the state E1 dash, these are forcefully brought back to G, so that this level always remains empty. As a result, the population inversion will always remain established, and you can get the de-excitation of the remaining four also. So as a result, the lasing action will never stop. So this is the advantage of the system having another level just above G. So now you can just understand, you can just appreciate that in case of Einstein's theory, we started the basics with a two-level system, then we talked about three-level system, and then this is a actually four-level system. In this four-level system, we have now noted that there will be four kinds of levels. One is G level, that is the ground level. Other is E level, that is the normal excited level. This is M level. This is also called UL level. This is called upper lasing level. And this L is also called lower lasing level, LL level. And both of these, UL and LL, are combinedly called lasing levels. So we can very easily give the definition of lasing levels. Lasing levels are those levels between which the lasing de-excitation takes place, means the stimulated emission comes out due to de-excitation between these two levels. So the stimulated emission here in our case comes from E2 dash to E1 dash, and both of these are called lasing levels. So this just completes my discussion about Einstein's theory of radiation. Another thing which we can just qualitatively try to understand is what is the importance of Einstein's coefficients. What is the importance of Einstein's coefficients? Okay, we know that RA was equal to V1 to N1 rho nu. So first of all, we have already found its unit, that its unit of B12 is Joule minus 1, S minus 2, and M3. Let me verify it. B12 will be equal to RA upon N1 rho nu. It was 1 upon M cube and S cube, S rate per unit volume per unit time. This was number of atoms per unit volume. This was energy per unit volume and per unit frequency. So this meter cube will get cancelled with meter cube. So it will be J minus 1, S minus 2, and M3. Okay, that is it. So this is the first thing, we have found its unit. Second is what is the definition of V12? We can very easily see that V12 is equal to RA upon N1 and rho nu. Now, in order to define V12, we must, if we assume that N1 is equal to 1 unit and rho nu is also equal to 1 unit, and then from this equation we can see that V12 is equal to RA. So this is just a numerical equivalence. These two are not equal to each other in totality, only their numerical values will be equal. Obviously, it is because of the fact that the unit of left hand side is this one and the unit of RA is not equal to that thing. So V12 is equal to RA is just a numerical equality, and this numerical equality is achieved when we assume that N1 is equal to 1 unit and rho nu is equal to 1 unit, and this helps me to define V12. So we can very easily define V12 as it is numerically equal to rate of absorption by the material whose number density in the ground state is 1 unit and which is irradiated by a beam whose energy density for a given frequency is also 1 unit. So that is the definition of B12. So we have found its unit, we have found its definition. Then we go to its significance. Suppose before significance we want to know on what factors does B12 depend. B12 depends upon what factors? So the answer is very simple. First of all, B12 is not same for different materials. For iron it will be different, for platinum it will be different, for ruby it will be different, for helium for helium it will be different, and so on. So first thing that you must remember is that B12 depends on the nature of material. Now suppose we choose a given material, so therefore nature is fixed. Now if nature is fixed, so we take two different samples of same material, but one material is at different temperature and another material is one sample, because material is the same in both of the cases. Suppose one sample is at a different temperature and another sample is at different temperature, then it is observed that the absorption of the light is not same at the different temperatures. Actually, the criteria is that the substance at lower temperature absorbs more energy than the substance at higher temperature. So the second factor over which B12 depends upon the temperature of the material. Now suppose we have a given sample at a given temperature, means I have fixed the nature of the material and I have fixed the temperature of material. What I now do, I will irradiate the material at a given temperature, firstly with light of smaller wavelength, that will be, let us say, in the blue region, and secondly I will irradiate the same material at same temperature with the light of larger wavelength, let us say red wavelength. It is observed that in both of the cases the absorption of the light by the material is different. So therefore the third factor over which B12 depends is that it depends upon the frequency or wavelength of incident light. Actually, this is something which we already know from the theory of black body radiation. Is same material does not absorb all wavelengths with equal probability. So every material absorbs one wavelength with large probability and another wavelength with small probability. Same is the case here. So currently something another which we must remember, that for a perfect reflector B12 will be 0 and for a perfect black body B12 will be maximum. I will not use the term unity because it has some unit, so therefore it will be maximum for perfect black body and it will be 0 for a perfect reflector. Now this is the third thing that we just observed about B12. Last part about B12 is that what is the significance of B12. Now we have found its unit, we have given its definition, we have known the factors over which B12 depends. Now let us say we fix temperature, we fix number density, and we fix let us say rho, that is we have a beam of light incident on a material whose coefficient of absorption B12 for Einstein coefficient B12 is having this value. Let us say this material has temperature T, its number density is N1. I will not talk about the temperature right now. Let us say its number density is N1 and the beam density is, let us say, rho nu. Now there is another material. This material is different from this one, but by changing the temperature, that is why I raised the temperature from here. Let us say by changing the temperature, because with change in temperature, N1 will change. Let us by changing the temperature, I make the value of number density of the second material same as that of the first material. Let us say same beam of light is incident on the material. However, its B12 is having some different value, B12 dash, let us. Now assume that one of them is smaller and one of them is bigger. Let us say we assume that B12 dash is greater than B12. Now the rate of absorption for this material will be RA and rate of absorption for this material will be RA dash. Now what will be RA dash upon RA? If you can see, RA dash will be equal to B12 dash N1 rho nu and it will be B12 N1 rho nu. It is due to the fact that in both of the materials, by making some suitable adjustments, I have kept N1 same and I have kept rho nu same. So these quantities will get cancelled out. Since I have assumed that B12 dash is greater than B12, therefore this quantity, actually it will be equal to B12 dash upon B12. Since B12 dash is greater than B12, so therefore this quantity will be greater than 1. So RA dash upon RA will be greater than 1, which implies that RA dash is greater than RA. Now this gives me the significance. So a material having larger value of B12 will absorb more light. So it can be just, I have actually already used this significance in my previous lecture. Now this is very clear from this example that the materials having large value of B12 absorb more light. So you can very easily give the significance that for a given material, the parameter B12 is representative of the probability of absorption of the light of given wavelength by a given material. Now let us go to importance of Einstein's coefficients. We know that Einstein's coefficients are 3. So I have given in detail the significance, definition, unit and the dependence of the parameters on various factors for B12. So I will just rush through the remaining two coefficients. It will be just an exercise for you people to understand the things in a liberal way, and I will be just writing the things and telling you that RSP is equal to A21 N2. First of all, its unit, A21 unit is Hertz, or it is second inverse. Secondly, its definition is A21 is equal to RSP upon N2. If we assume N2 is equal to 1 unit, then A21 is equal to RSP. Again, this is a numerical equivalence. So we can define A21 as equal to rate of spontaneous emission by a given material whose number density in the exciter level is unity. Similarly, what are the factors on which it depends? Number one, it depends upon nature of material. Number two, it depends upon the temperature of the material. And number three, it depends upon the wavelength of the incident light. These three factors will remain same. Last one, what is the importance of A21? So I can very simply see that just to say to you, it will be just your problem to understand in the same way that for given value of N2, RSP will be proportional to A21. So more is A21, more will be RSP. So therefore A21 represents the probability of spontaneous emission by a given material. Kindly remember that in case of lasers, the spontaneous emission is not desired. So in order to decrease spontaneous emission, we have to choose a material for which A21 is as small as possible. Theoretically, its value should be 0, because A21, if it becomes 0, then RSP will be 0. Therefore, whole of the light that will come out of the material will be of stimulated manner. But this is not practically possible. But practically, we can keep A21 as small as possible. Next is again about V1, V21. So I will leave it for you. I will just write the equation. RST is actually V21 and 2 and rho nu. So its unit will be same as that of V12. Its significance is that it tells us the probability of stimulated emission from a material. We also have derived in the previous lecture that V12 and V21 are equal. It means good absorbers are good emitters, because V12 is probability of absorption and V21 is probability of stimulated emission. So if V12 is large, means if a material absorbs large amount of light, only that material can emit large amount of light. So next is its unit that we already know, J-1, S-2, the wavelength of the incident radiation, and this is how we can just give significance to the Einstein's coefficients. Next, I will turn my attention to the lifetime of an energy state. So these are the smaller topics which we need for the better understanding of the laser chapter. So lifetime of an energy state. I mentioned in my previous lectures that when an atom is excited to some higher energy level, then the excited states are not longer lived, these are short lived. So every excited atom again comes back to the ground level after a certain interval of time. So if we have N0 atoms initially in the sample, all of them are in the ground level, and we just provide energy to the materials, and then what will happen, these energy, let me take the example in another way. Suppose there is a sample and I provide some energy to the sample, and when I provide some energy to the sample, then due to that energy, N0 number of atoms, they go to the excited state. And when these atoms go to the excited state, then we stop giving energy. When we stop giving energy, at that instant, just at that instant, the total number of atoms in the excited state were N0. As the time will pass, the atoms will start de-exciting. Kindly remember, all atoms do not de-excite at the same instant of time. Some atoms de-excite almost as soon as the energy is stopped. Some may de-excite even after 1 hour. Some may de-excite after, let us say, 1 day, and some may not de-excite even for years. So it is just like a phenomenon of radioactivity. So after a time T has been elapsed, then the total number of atoms remaining back in the excited level will be reduced due to de-excitation. Let us say the number of atoms remaining back in the excited state are N, which is obviously a number smaller than N0. It is observed that N decreases exponentially, and the relation is N is equal to N0 e raised to power minus tau and T. This is very similar. This is very similar to the what we call as radioactivity kela, in which we wrote n is equal to n0 e raised to power minus lambda t in your higher secondary classes, which we have studied in your class. There lambda was called disintegration constant or decay constant. Here I would call tau to be characteristic time for the time being. So I want to this characteristic time is different for different materials. I just want to define what is tau. What is going to happen if we assume that time elapsed is equal to 1 by capital T. Then what is going to happen? N will be equal to N0. Sorry, this relation I did not write correct. It is equal to actually minus T upon tau. Now this will be, because the argument of the exponents are always unitless. So if tau has to be the unit of time, it must be in the denominator. So if I put T is equal to tau, now these two relations are very similar again. There is no problem in understanding that. The only difference is that this was called disintegration constant and its unit was reciprocal of time. It is characteristic time and its unit is the same as that of the unit of time. So if I put T is equal to tau, then what is going to happen? N will be equal to N0 e raised to power minus 1. It is therefore N0 upon E, and we know that this is E is 2.7183. Therefore this will become actually 0.318 of N0, or you can say it is 31.8% of N0. So this characteristic time is called lifetime of a state. So from this mathematical calculation, we can define lifetime of a state is that time in which the number of atoms in the excited state reduced to 1 by E of the value of at 0 interval. So in that, if I have, let us say, T, let us say tau for a normal excited state, I told you that tau is of the order of 10 raised to power minus 8 seconds. So what is the meaning of this? That if I have 1000 atoms in excited state, then 0.318 of N0 will become 300 atoms. I have assumed the tau is equal to 10 raised to power minus 8 seconds. Therefore, after 10 raised to power minus 8 seconds, the number of atoms in the excited state will remain 318. It means 682 atoms have de-excited. So I deliberately took a different definition of, kindly remember, it is almost very close to the total number of atoms de-exciting. I took that example there deliberately in my previous lecture, that lifetime is the time up to which an atom can stay in that state. However, that was not correct, but still it did not have any impact on the explanations that I gave you by choosing that some deformed definition of the lifetime. This is the correct definition of the lifetime of a state. So please remember this for your further reference. Next, I would like to discuss with you that in case of laser, the intensity of light grows as seed photons travel in the material. Now, what is happening? So, suppose this is the sample. Let us say seed photon travels from here. So, here the value becomes, let us say, double. Here it becomes, let us say, 4 times due to stimulated emission, and the intensity grows. Let us say the intensity is I here, I0 here, and intensity is I here. Now, what happens for a normal material when we pass energy through any substance? Then what happens? Let us say energy entering is E0, energy coming out is E. Most of the times E is smaller than E0. If I write here power, then the same relation applicable for power. If I write here intensity, then the same relation is applicable for intensity. And we know that the relation, famous relation is I is equal to I0 e raised to power minus mu x. Here mu is called absorption coefficient, because whenever we pass beam of photons through a material, the material absorbs some of these photons, and the beam of photons that comes or exits from the material is of smaller intensity than that of the incident intensity, and the intensity again decays exponentially, and the characteristic parameter there is mu. It is called absorption coefficient. So this is the graph for a material. The intensity decays with the distance. However, in case of lasers, the graph is not like this, because a seed photon initiates a process due to which the number of photons start multiplying. Instead of decaying, they start multiplying, and the graph is actually this. So both of these are exponential. If I just write same relation for here, I is equal to I0 e raised to power minus mu x, then this same relation can represent this graph provided that mu is negative. It means we can understand that laser material acts just like a material having a negative absorption coefficient, because instead of absorbing the light, it multiplies the intensity of the light. This we must remember. So this was all about Einstein's theory of radiation. So next I would just like to give you the classification of the lasers. So because it is enough time for today's lecture, I would just start with you a small topic, that is the classification of lasers on the basis of energy level diagram. So this is just like a sort of reverse engineering to the Einstein theory of radiation. So because I started Einstein theory of radiation with a 2-level system, then initial conditions for stimulated emission were obtained from the 2-level system. Then we found that it is not good enough to be commercially useful due to certain limitations. Therefore, we added artificially an intermediate state, that is metastable state, and then we just created a 4th state, but just above G, and this is how the Einstein theory of radiation was completed, from 2-level to 3-level to 4-level. Now it is just reverse engineering. I will start from 4-level, then go to 3-level, then go to 2-level. It will be just a recapitulation of Einstein theory in the reverse order. However, there will be certain things which will become more clear to you after just discussing with the discussion of this topic. So I advise you not to skip this part, and because it will be helpful for you to having a better understanding of the Einstein's theory. And it is in fact in itself a different topic also. So because I am not going to use any mathematics, I will be just taking some concepts into mind and I will try to discuss that with you. Okay, on the basis of the energy level diagram, we can have three types of lasers. The first type of laser is called four level system. Four level laser. So essentially what happens in case of the four level laser, we have four important energy levels. So this energy level is called G level, this is called E level, this is called UL, this is called LL. G stands for ground level, E stands for excited level, normal excited level, UL stands for upper lasing level, and LL stands for lower lasing level. So I would use a double arrow of this shape giving external energy, and it is a topic of discussion in the later lectures that it is not necessary to always supply photons on the material. Beam of photons may be good for creating population inversion and producing lasing action from solid material. However, all lasing materials may not be in the solid form, so it is not always necessary, rather not convenient to use a beam of light for pumping. So therefore, I have avoided now here to show incident beam of photons. I have used a double arrow of this shape that just tells that the energy coming from the pump, any device which is providing this energy, will be called pump. So this can be given energy in different ways. So I will discuss what are the various important ways of providing energy to the material in separate lecture. For the time being, you just observe that this is energy which is incident on the material, and this energy is synchronized between G and E level. Means after getting this energy, any electron which gets energy from the pump is excited from G level to E level. Okay, what is going to happen? Now between E and UL, the excitation is allowed, and let us say the energy of this is E2, the energy of this is E2 dash, the energy of this is E1 dash, the energy of this is E1. So from here to here, the atoms will come by themselves, and the process will be spontaneous or non-radiative process. And this is a metastable state. I can also call it to be M, and its lifetime is of the order of minus 10 raised to the power minus 3 seconds. Its lifetime will be of the order of 10 raised to the power minus 8 seconds. So this lifetime it depends on the nature of the level. If it is a metastable state, then its lifetime can be large, of the order of 10 raised to the power minus 3 seconds. If it is a normal excited state, just like E, then its lifetime may be small. It is desired for us that it should have a small lifetime, but unfortunately, any four-level system that we use, in most of the cases, this is an extraordinary, highly stable level, because it is very close to the ground level, and the lifetime of the ground level is infinite, because any atom which is in the ground level can stay there for infinite time, and this level is just above the ground level. So it is in most of the cases, it is a long-lived case. So it is against our desired expectation. So we want actually it to be short-lived, but most of the times it is not shocking. Okay, what will happen? So pump will take atoms from here to here. Let us again take that example. Suppose there are 100 atoms in the material. Out of 100, let us say only 90 are here, 10 go here. Out of 10, let us say 9 go here, and this is 1 here. And since the number of atoms here are 0, so what will be the important property? That population inversion will be established between this level and this level as soon as the pumping will be achieved. And out of these 9, let us say 1 de-excitation takes place due to one of the electron leaving UL, and here it will become 8. This will become 1 for the time being, and due to induced de-excitation, we will bring that 1 back here. So this 1 will come here, this will remain 0, and a seed photon will be produced. This seed photon will have energy E2 dash minus E1 dash, and it is still traveling in the material. And when it is traveling in the material, there are still, as per the given example, there are still 8 atoms in the M level. So when it will strike with these 8 atoms, although when it will strike with one of these 8 atoms, then although that atom still not have completed time 10 to the power minus 3 seconds, but because of the collision, it will be forcefully de-excited, and due to law of conservation of linear momentum, the number of photons will become 2. And this, out of these 2 photons, 1 will be the seed photon and 1 will be the stimulated photon. Now these 2 photons will have exactly same energy, exactly same state of coherence, and these will have same direction. And when these 2 photons will be traveling through the material, then they can again strike just as the first initially seed photons struck, and the number of photons will become 4 and then 8 and so on, and as a result the process will continue. So this is how a 4-level laser works. This was a conceptual thing. Now what is important or extra thing that I am trying to tell you is that since we want efficient pumping, kindly remember this E level, I have shown it by a sharp line. So for efficient pumping, it is good for us that it should be a broadband. When it is a broadband, then since this pumping may contain different energy quantas, so when it is usually, you can say, polychromatic, let us say it is a beam of light, then it will be polychromatic. Otherwise you can say it will be non-resonating energy. So since if it is a big band, then photons from this pumping source or any energy quanta from this pumping source which is of different energy will be efficiently absorbed. Now you can see I have shown here 4 different transitions, one to the bottom, 2 in between the band, and last one to the top of the band. All these 4 transitions or excitations will require different energy, and since this is not a laser source, this is an ordinary light source, or this may be an ordinary another source, electric source, or it can be direct pumping source, it can be chemical source which will be producing light of different quantas, and different quantas of different energy will be very easily absorbed by this E level if it is a broadband. So therefore, for a good or efficient pumping, we desire E level to be a broadband. Now what is going to happen? This UL level, we can think whether it should be a broadband or it should be a sharp state. Now suppose if it is a broadband, just like E, then what is going to happen? The de-excitation from E to UL will be like this. So therefore this broadband will be filled, and the seed photons will be produced, they will be of different wavelength. One, let us say, from here, another from the middle of the band, and another from this. So these 3D excitations will produce photons of different wavelength or different energy or different frequency. Since this between UL and LL, we have a lasing mechanism taking place. Therefore, we will not desire this to happen because laser light is always preferred to be monochromatic. And if we take this kind of band in case of upper lasing level, then the chances of light emitted to be monochromatic will be very grim. So therefore, it is not desired to have a band. So in contrast to E, we desire that for a better lasing mechanism to take place, UL should be a sharp state. Upper lasing level should be a sharp state. Now, if you have understood the story that I have just told you, you can very well appreciate that just as UL should be sharp state, in the same way LL should also be sharp state. This is what we desire. It may or may not be fulfilled by making the actual lasers, but theoretically, for a good lasing action to take place, this is our requirement. We must have the knowledge of these things, that upper lasing level preferably should be sharp, lower lasing level preferably should be sharp, and E level preferably should be a band. And what is another important thing we should remember, that I will define a parameter now, eta, which is called quantum efficiency. It is the ratio of energy of lasing photon per emission, that is E2 dash minus E1 dash. Kindly remember, the lasing process is taking place between UL and LL. So the photon which is stimulatedly produced has energy E2 dash minus E1 dash. I think I wrote here wrong. It is E2 dash minus E1 dash. So next, it is the ratio of energy or lasing of the photon per lasing transition to the energy of absorbed per excitation. Now, since the excitation is from G to E, so this energy is obviously E2 minus E1. So this is the efficiency, quantum efficiency of a laser, and in case of 4-level laser, we can very easily see that quantum efficiency is smaller. So therefore, it is poor quantum efficiency. So this is the disadvantage of a 4-level lasing system, and that the quantum efficiency of the laser light from a 4-level laser is decreased. However, this is only a small disadvantage, because if I have, let us say, 100% quantum efficiency, let us say, and because in case of 2-level system, this quantum efficiency will be 100%, because both E1, E2 will be acting as E2 dash, E1 will be acting as E1 dash. So in that case, quantum efficiency will be high, but because the pump will be working in cycles, the intensity of the light will be small. So there will be, let us say, this energy difference is 10 eV in case of 2-level system. So energy absorbed per photon will be 10 eV, energy emitted per photon will be 10 eV, quantum efficiency will be equal to 1, that is 100%. However, there will be smaller intensity in case of 2-level system, that I have already discussed with you in my previous lecture. So if I have just got, let us say 100 D excitations, then therefore I will be just getting 100 into 10 is equal to 1000 electron volt beam energy. This is the beam energy. On the other hand, in case of 4-level system, let us say, because of this gap up and this gap down, let us say this energy difference is only 8 eV. Now what will be my quantum efficiency? It will be 8 eV by 10 eV. Now it will be only 0.8 or 80%. But however, the number, this level is metastable state, and the number of atoms which can stay here is of the order of 10 raised to power 5 times more as compared to the number of atoms that can stay here. As a result, intensity will be of the order of 10 raised to power 5 times more than that of normal light. So therefore, the beam energy will be equal to 10 raised to power 5, which is the multiplication factor, into 100, which is same as I have taken here. I assume that per cycle only 100 photons are excited by the pump, and the efficiency, that is 0.8. This will make it to be 80 into 10 raised to power 5 electron volt. Now you can very easily see that 80 into 10 raised to power 5 eV is much greater than 1000 eV. Although the excitation per photon has decreased, but beam energy has increased manifold. So this is therefore an advantage instead of disadvantage. So a 4-level system can produce very powerful lasing beam, but obviously the photon energy will be smaller than that of incident energy per excitation. So second thing which we have learned from a 4-level system is that the energy of the light that we will be obtaining from a 4-level system will be in a continuous manner. So 4-level system will always give you light in a continuous fashion, and that is the advantage of the 4-level system. So most of the 4-level lasers are continuous wave lasers, and next advantage of 4-level system is that it acts instantaneously. So there is almost no time gap between the starting of the pumping mechanism and emission of the laser light. So both of the processes start at the same instant. So I hope I have discussed this thing with you in quite a good detail. This was the discussion of 4-level laser. In the next lecture, I will start with you 3-level laser. That is a part of this lecture, because the time is enough for today's lecture. I will preferably like to stop here, and I will continue this lecture for 3-level and 2-level lasers. What are the deficiencies of 3-level laser and 2-level laser? Although we have discussed it in the Einstein theory, but it is good to compare these things in the reverse order for better understanding. So I would stop here. Till then, it's goodbye from me. Thank you. Thanks a lot.